Here is another problem for analyzing an heat exchanger. So let's say we have a shell and tube heat exchanger. So this heat exchanger have already existed. One shell pass and 8 tube passes heat exchanger. And in these heat exchangers, the tubes are thin walled and are made of copper with the internal diameter of 1.4 centimeter. The length of each tube pass is 5 centimeter. And we have the corresponding heat transfer coefficients of inner and outer surface of tube at 636 and 605 watt per meter square Kelvin. Now, imagine that you're going to provide some consultation services to a company in terms of heat exchanger, and they have this heat exchanger in their storage purchased previously, or it was in a process that was just discontinued, and they have this heat exchanger. So all the parameters of heat exchangers is given. Of course, the convective heat transfer coefficient would depends on the type of flow that we have, and you have seen from the forced convection the flow rate and the Reynolds number. But let's say for the process that they're going to use, these are the numbers. Of course, based on the flow rate and the flow regime and the Reynolds number and other parameters that you have seen before, we can determine what would be the heat transfer coefficients. But right now, the plan here is that they're going to use, they're suggesting to use this heat exchanger for cooling of hot oil, maybe from an engine or other processes by water. Okay. Now they know the water flows through the tube. So this is another piece of information at the rate of 0.2 kilogram per second. And the oil is through the shell at the rate of 0.3 kilogram per second. Knowing these flow rates, the mass flow rates, we can get the Reynolds number and then do the calculations for HI and HO. If they are not given, the heat transfer coefficient. Now the water and oil enters at temperature, they know the temperature of 20 and 150 degrees C. So your job here is to determine the rate of heat transfer. Yes, the rate of heat transfer in this heat exchanger, and mainly the outlet temperatures of water and oil. So let's say if you have this heat exchanger and you know these are going to be the cold and hot stream flow rates and the inlet temperature for this specific heat exchanger, what we would get in the outlet. So I'm going to just quickly draw a schematic of, it says, one shell, 8 tube pass. So let's assume this is the inlet for the shell. And this is the outlet for the shell. Okay, so this is the shell of the system, and then we have 8 tube passes. Perfect. So we have the water. Water gets in, that's a cold stream at 0.2 kg per second and temperature of 20 degrees C. The water goes out, we don't know at which temperature. And then we have this hot oil. So oil is getting in at 0.3 kg per second and at 150 degrees C in the shell, and that's the outlet of oil. So this is the heat exchanger that we are dealing with. The known parameters are the inlet temperature for the hot, 150 degrees C, the inlet temperature for the cold, 20 degrees C. We know the mass flow rate of the hot, 0.3 kilogram per second, the mass flow rate for the cold, 0.2 kilogram per second. And what else do we know? We know the internal heat transfer coefficient, convective heat transfer coefficient inside the pipe is 636 watts per meter square Kelvin, and the outer one is 605 square Kelvin. The length is 5 meter, and the diameter of the tubes are 1.5, 1.4 centimeters. So these are the known parameters. So this is the length of the pipe that we have, L, which is 5 meter. In terms of assumptions, assume steady state condition. And negligible heat loss. Of course, negligible radiation too, but negligible tube thickness. And we are using copper for the tube, so it has a high thermal conductivity. High thermal conductivity of tube material. Or what does that mean is it provides really minimum resistance by conduction to the transfer of heat from the hot to the cold. Now, constant properties. And constant, let's assume constant HI and HO. And of course, there is really no falling here as reported. So this is the heat exchanger. These are all the assumptions that we are going to make, and these are the known values that we have. And let's assume we have the properties, or we can read the properties at the temperatures that we have. And what we need here is the CPC for the cold, which is 1480 joule per kilogram Kelvin, and CPNH is 2130 joule per kilogram Kelvin. Okay, so these are the parameters that we have. Now we can use for this heat exchanger. It doesn't say which technique to use, and we know there are two ways to do the heat exchanger analysis, either LMTD or effectiveness NTU. Now for this problem, since we don't know really the outlet temperatures, we can use LMTD. LMTD requires really long iterations, and it becomes a really tedious procedure. So we're not going to use that one. So we use effectiveness NTU technique. Okay, and for doing that, the first step was to determine the C min. And for doing that, we need to find out CH, which is m.h, CPNH, 0.3, 2130. It's going to be 6390 watt per Kelvin. And if I evaluate CC, m.c, CPNC is 0.24180. 8360 watt per Kelvin. So out of the two, I can find out what is C min is going to be the hot stream, which is 6390 Kelvin. Capacity ratio C min over C max 390, 8360, which is 0.764. Okay, so I have C here. Now I can find Q max. I don't need the outlet temperature for that. That's going to be C TH and I minus TC and I, which will be 6390 times 150 minus 20, 83.1 kilowatt. So this is going to be the maximum possible heat transfer coefficient. Now heat transfer rate. Now area is n pi dl. So this is the surface area that each of these tubes provide. Okay, I'm assuming these are like 5-meter lengths. We have 8 of them, so n is going to be 8. So it would be n 8 pi. The diameter was 0.14 meter and L was 5, so 1.76 meter square. So this is the total surface area. We have HI and HO, so I can evaluate U. Since we are using a high conductive tube with a very thin wall, then we can assume the main resistance heat transfer or the convective heat transfer inside and outside the tube. And we have 1636 plus 1605 to the power of -1, which gives us 310.05 watt per meter Kelvin. So having area and U and C of mean, I can find NTU. NTU is UA divided by C. So it's going to be 310.05. Area was 1.76 meters square. Mean is 639. That's going to be 0.854. So I have C, which is 0.764. That's what we found here. And then I have NTU, which is 0.854. Now, having these two, I can go to the plot and correlations to find out the effect. So if I look at the proper plot for one shell pass, but multiple tube passes, like something like that. So this is the shell, and this just shows you for 2 tube pass, but it's applicable for 2, 4, 6, 8, or any number of that. I have the relationship between epsilon and NTU plot of that versus different C. So here NTU is 8.4. So if it's 8, so let's say this is going to be a lot of that. Now I draw that one to 7.6 something. So if there are really huge differences, then we need to read, like let's say, the number between the two and do the interpolations. But here, in fact, I can say this is 0.764, and then I can read the plotting. So I can read the value of effectiveness. So effectiveness from this chart is going to be about 0.47. Now, having this effectiveness, I can find out the heat flow rate, epsilon Q max, which is going to be 0.47, and Q max evaluated before 83.1 kilowatts. So it's going to be 39.1 kilowatt. So this is going to be the actual heat transfer rate that happens inside this heat exchanger. By having that one, I can simply use the energy balance for the hot and cold stream and find out the outlet temperature. So Q is CC, TCO minus TCNI. From here, TCNO is going to be 20 plus 39.1 divided by 836. So it's going to be 66.8 degrees C. That's going to be the outlet temperature for the cold stream for the water. And similarly, I can find out Q for C, TH, TH and I minus TH and O, which is going to be TH and O would be 150 minus 39.1 divided by 0.639, which will be 88.8. degrees C. So this is going to be the outlet temperature for the hot stream. So we can cool down the oil from 150 degrees C to 88 degree by using a cold stream of cold water that enters this specific heat exchanger at 20 degrees C and goes out at 66 degrees C. And the analysis is done. No requirement for iterations whatsoever.